radar range equation. So we are considering a antenna which is isotropic antenna. Suppose this is the antenna, or it is radiating in all the direction. Okay, so this is the antenna which is radiating in all the direction, and the distance from the antenna or the radar to the target is, let us say, r. This is the target and this distance is r. So we know that this antenna or the transmitter in the radar system transmits very high power. So it is transmitting a high power, let us say PT. So the transmitted power is given by transmitter generates power, let us say PT. Okay, so this is the transmitter which is generating the power PT. Now if this antenna is isotropic, that's why it is radiating in all the direction, and we are also considering that actually we want to have a high gain antenna because we want to transmit a power in a particular direction, because where we expect the target in that particular side, we want to transmit the high power with high directivity in fact. Okay, so that means we should have a antenna that should be a very high directive gain, or you can say a very high power gain. So if the gain of the antenna we consider, then this transmitted power will be multiplied with the gain to get the high directivity in such particular direction. So if the gain of the antenna is G, then what is the total transmitted power will be PT into G. So if the gain of antenna is denoted by G and antenna is lossless, we are considering that this antenna is made up of a perfect conducting material. So there is no conduction losses, or there is no radiation losses, or there is no conduction losses, and that's why the efficiency is 1. That is the radiation efficiency which we have studied in the chapter of antenna. So you are familiar about what is the meaning of antenna is lossless. So if the antenna is lossless, then the power radiated by the antenna, is PT into G, because we know that whatever is radiated in the free space, that should be multiplied with the gain, because we want to have a very high directive power or high directive gain of the antenna. Okay, so if you are having an antenna like this, suppose as we studied in the antenna chapter, so if this is the antenna, then the radiated power, this is the radiated power, and this is the power which is giving in the input, and in the input of the antenna we are giving the transmitted power, okay, which is generated by the transmitter. So the transmitter generates a power PT, the transmitter generates power PT which is input to the antenna, and because this antenna is lossless, whatever input you are giving is the radiated, and because this antenna is having a certain gain, so this radiated power is actually the input power multiplied with gain. So this radiated power is nothing but the input power, which is the transmitter power multiplied with gain. So this is the power which is actually radiating in the free space. Now since this is, we are considering as an isotropic antenna, so it is radiating in all the directions, so we can have a imagination of a sphere of radius r. If you want to calculate the power density at distance r, because it is transmitting a power, so we want to calculate the power intercept with this target which is at distance r. So it means you want to calculate the power density at distance r. So what is the power density at distance r? So power density at distance r, power density at distance r is given by power per unit area. What is the power density? So power density is power per unit area, and how much power it is transmitting. So the transmitted power is actually, or the radiated power is actually PT into G. So it is equal to PT into G, which is the radiated power at any distance r, which is considered as a sphere. You can imagine a sphere of radius r, so it will radiate in all the direction with the of the distance r. So the power density is the PT into G and the surface area of the sphere, because we want to calculate the power per unit area and we are having the sphere, so the surface area would be 4 pi r square. So this is the actual power density which is transmitting or at the distance r. So now if the target has, if target has radar cross section area, radar cross section area is equal to sigma meter square, then how much power it receives, the target receives. So the power received, the power absorbed by the target is, because we are having the power density which is given as power per unit area, that means its unit is watt per meter square, and when you multiply with the meter square, that means the area of the target or the radar cross section area of the target, this sigma is known as radar cross section area of target. So this is PT into G into 4 pi r square. This is the watt per meter square, that is watt per meter square, and multiplied with sigma meter square. So it will give you PT into G into sigma divided by 4 pi r square watt. You can cancel this meter square. That means this is the power which you are getting. This is the power which you are getting at the target, and this power is radiated in all the direction and it is coming back to the antenna, and when it reaches to the radar antenna, it is received by the aperture area of the radar antenna. So if the effective aperture area of the radar antenna by which we transmitted the power, the same antenna if we are using, so this, and during the transmission we are more interested about the gain of the transmitting antenna, and during the reception we are more interested in the how much portion of the antenna the power is incidented, that means the area in which the power is incidenting. So the effective aperture area of antenna is AE, or you can consider first let us say not talking about the effective aperture area right now. So we are having the power and it is going back, okay, so it is going back to the radar system. So it has been again traveled a distance of r. So again we have to calculate the power density first, because what is the use of this area which we were writing? The use of the area is to calculate the power, but here we are having already the power and it is re-radiated. So when it is re-radiated, it is moving towards the radar station. So when it is moving towards the radar station, it is traveling a distance of r. So again it is traveling a distance of r. So if you calculate the power density again at a distance r or at the radar station, so power density at radar station is, again this is the power, which is Pt into g into sigma divided by 4 pi r square, and that should be again divided with the 4 pi r square. Now you have got the power density, watt per meter square. Okay, now if we consider, because the power has been reached, the radiated power, which is known as echo signal, has been reached to the radar system. So when it has been reached to the radar system, now if we multiply with the effective area of the radar in which this power is incidenting, the power received can be calculated. So if the effective aperture area of antenna, which we know what is the value of this effective aperture area, in the chapter of the antenna we have studied that if the effective aperture area of the radar antenna, that is the transmitting antenna, is AE, which is in meter square, then what is the power received? So power received by the antenna, power received at the radar station is given by PR, this is the received power, and the power density we have got, if you multiply with the area you will get the watt, that means the received power. So what it would be, Pt into g into sigma 4 pi r square whole square, because there are 2 times 4 pi r square in the denominator, and multiplied with the effective aperture area, so that is AE, A in subscript E. So this is the received power. This is the received power in the radar system. But here we have to calculate only the range of the target. So what is the range? What is the range of the target? So the range of the target is corresponding to the minimum detectable power, because when you are transmitting a power, so it is intercepting with the target, and when it is intercepting with the target, some power is reflected back, and if you won't get any power at the radar station, then how will you calculate the range of the target? So because until you get the echo signal, you will not be able to recognize the target or find the location of the target. So what you have to do is, you have to get at least some power from the target. That is called the minimum power or the minimum received power, and also known as minimum detectable power. The minimum power which this radar station can detect can give you the maximum range. Until you get the received power, you are not able to calculate the range of the target. So suppose this target is at this distance, and when you transmit the power and it is reflected back from here, and that is the power which is the minimum power this radar can detect. So if the target is moved more or farther away from the station, so it moves away from this. So if you transmit the power, it is intercepting with the target, but it is not coming back to the radar station. So you will not be able to determine the range of the target. So always remember, the minimum detectable power that can be detected from the target can give you the maximum range that you can calculate in the radar system. So this power, received power, should be minimum detectable power. So this received power should be equal to the minimum detectable power, and when you get the minimum detectable power, this R is equal to the maximum range, will be the maximum. So if you calculate the value, this minimum detectable powers, that is denoted by S minimum, this is denoted by S minimum, is equal to Pt into G into sigma into Ae divided by 16 pi square and r to the power 4. So the R max, in fact, because this is equal to the maximum detectable power. Okay, so this R maximum to the power 4 is Pt into G into sigma into Ae divided by 16 pi square into S minimum, or the maximum range which we can get is the Pt G sigma Ae divided by 16 pi square and S minimum whole to the power 1 by 4, and this is called a radar range equation. This is called radar range equation. So it is very easy to derive this. What you have to do is, first of all, you have to consider the transmitted power that is generated at the transmitter, which is Pt. So if it is transmitting through antenna, you should be multiplied with the gain. So this is the Pt into G, which is actually radiated by the antenna. Now, at which point you are calculating the power? So let us say if we want to calculate the power at the target, right? So the distance of the target from the radar station is r. So you have to calculate the power density at r, which is Pt into G divided by 4 pi r square. Now the target has some cross-sectional area, so that is known as the cross-section area of the target, radar cross-section area of the target. So you should multiply with the radar cross-section area, so you will get the power again. Now again, when you are coming sending back, or you are getting the echo signal, right? So from the target it is re-radiated. So if the power is radiated again, so where you want to calculate this echo power, that is again at the radar station only. And if the radar station is again at the distance r, we have to calculate the power density again. So that is Pt into G into sigma, which is the radar cross section area, divided by 4 pi r square whole square. That is the power density at the radar station again. Now at the radar station, when we are talking about the received power, we will multiply with its effective aperture area. So once you multiply with the effective aperture area, you will get the received power, and that is it. Now we are saying that about the maximum range, so that is corresponding to the minimum detectable power. That is not necessary to consider, that is just the concept. You should know what is the meaning of the minimum detectable power, because corresponding to the minimum detectable power we will get the maximum range. Beyond this range, if the target will move, you will not get any signal from the target, and that's why you will not be able to locate the target, and you will not be able to tell about the range of the target. So that is the main concept. Actually, to derive the equation, you should write equation up to this point only, then you will transfer the range in the left hand side, you will get the equation of range, and that is the radar range equation, which is very simple. Okay, now suppose we want to write the whole equation in terms of gain of the transmitting antenna, because we are using the same antenna for the transmission and reception purpose. So that is why we can have the relation between the effective aperture area of this antenna with the gain of the antenna, which is lambda square upon 4 pi into gain. So this gain of the antenna and this effective aperture of antenna can be related, because we are talking about the same antenna. So if you want to write this maximum range in terms of gain, suppose, so the relation would be, if you want to write in terms of gain, so that means you have to replace this effective aperture area in terms of gain, and that is lambda square divided by 4 pi into gain. This is in the numerator, and divided by, this is 4 pi whole square, right? 16 pi square, that means 4 pi whole square, and this is the minimum detectable power, which you can write it as received power as well, PR, which is 1 by 4 here. So when you write it from here you will get the maximum range equal to Pt into g square into sigma into lambda square divided by 4 pi whole cube and S minimum whole to the power how much? 1 by 4. So this is the maximum range or the range equation in terms of gain of the antenna. So if I keep other parameter constant, this range is proportional to root G, isn't it? 1 by 4. So this gain is proportional to root G. So that is the relation. Suppose in the question it is asked if I am changing the gain of the antenna by 16, if I am increasing the gain of the antenna by a factor of 16, then what would be the range of the antenna, or by which factor the range of the antenna will change. So if you are increasing the gain of the antenna by a factor of 16, that means root 16, that will be give you 4. So it means the range of the radar has been increased by a factor of 4 in this way, because it is directly proportional. So that is the advantage of converting in the terms of gain. And just similarly, you can convert the whole equation of radar range equation in terms of effective aperture area. So this effective aperture area can be written as, this is Pt, and G can be written as 4 pi by lambda square into Ae into sigma into Ae again divided by 4 pi whole square into minimum detectable power and whole to the power 1 by 4. Okay. Now this is in the numerator. So this 4 pi and this 4 pi will get cancelled, and we will get here a R max equal to Pt into sigma into Ae square divided by lambda square 4 pi lambda square. 4 pi will be left, and this lambda square will go into the denominator, and S minimum and whole to the power 1 by 4. This would be the range equation. So here we can see that this, if we keep other parameter constant, then this maximum range is directly proportional to root Ae. So if I change the effective aperture area, what will be the change in the radar? We can get from here, or you can also write this, because we consider the parabolic dish antenna. So this effective aperture area is given by pi d square, or pi d square by 4, or we can write pi r square. So we can say that this maximum range is directly proportional to d square or r square, or root over r square, or simply the d and r. Okay, so that means if we change the diameter of the antenna by 2, then the range is also double. In this way we can relate it. Okay, so this is the important equation. And from this equation you can have many questions in the GATE as well as in the different exam like ISRO and DRDO. And here this is the different equation of the radar range equation according to the different parameters. So you have to remember this only, and how to derive this that you should know. And from here you can convert either in terms of gain of the antenna, or you can convert in the effective aperture of the antenna. Now suppose if you want to derive this for a different antenna, suppose the transmitting antenna and the receiving antenna is different, then how can you derive this received power? That is again very simple, and you can derive it only in one line. Okay, so let's see how to derive when the range is different and also the transmitting and the receiving antenna is different. Okay, suppose this is the transmitter, okay, and this is the transmitting antenna. and suppose it is the receiver and this is the receiving antenna. And here is the target. Suppose the distance between the transmitting antenna and the target is R1 and the distance between the target and the receiving antenna is R2. Okay, so we don't know about the exact distance. We are considering the distance between the transmitter and the target is the R1, that is this is the radar station and this is the target. This distance is R1 and this antenna is now located somewhere else. So suppose this antenna, the separate receiving antenna is located somewhere here. So this distance from the target to the antenna is R2. This antenna can be anywhere, the distance is given to you, that is R2. Then how do you calculate how much power you are receiving at the receiver? Then that is very simple, because we know that if the transmitter is generating the power PT, so suppose this is generating a power PT, then it is multiplied with the gain of the antenna of the transmitting antenna. Okay, so this is multiplied with the gain of transmitting antenna. Now once you get the power transmitted by the antenna or the power radiated by the antenna, we have to calculate the power density at the target. So to calculate the power density, we divide it by 4 pi r1 square, that is the power density, and we always calculate the surface area of sphere because we consider the radiation is in all the direction. 4 pi r1 square. Now it is intercepting with the effective aperture area, or sorry, it is intercepting with the radar cross section area of the target. So if the radar cross section area of target is again sigma meter square, then it will be multiplied with the sigma. Okay, so from here we have got the power which is absorbed by the target and it is re-radiated in all the direction and re-radiated, and we want to receive at the distance of R2. So that means you have to divide it by 4 pi R2 square, that is you have to calculate the power density again at the receiving antenna. So to calculate this, we divide it by 4 pi R2 square. Now once the power has been reached to the receiving antenna, you want to get the power, so for that you have to multiply with the effective aperture area of the receiving antenna. So you have to multiply with the AE of receiving antenna. So here this GT and AE are not related to each other. So this is not related to each other because these two antenna are different, so their relation may be different. So it is related to the effective aperture area of the transmitting antenna and it can be related to the gain of the receiving antenna, but both are having the same relationship. The relationship is same, but they are not related to each other. This antenna will be having some different effective aperture area and this antenna can have a different gain. So this is the power received at the receiver. If you want to calculate here the received power, then this would be the answer. And here we have considered the two separate antenna for the transmission and the reception, and the distance from the transmission to target and target to the receiver is also different, that is R1 and R2. So in this way we write the radar range equation.